Alright, welcome back everybody. In this video we're going to continue looking at the examples from the Graphing Polar Coordinates lesson. We're going to look here in example 3. We're going to draw the graph of r equals 1 minus the cosine of theta. And in order to get this graph to not be all crammed real tight in the middle, I'm going to let each circle on the graph be equal to 0.25 units. So that my graph here is going from -2 to 2 in both directions when we look at it from a Cartesian standpoint. Alright, so in order to draw the graph of r equals 1 minus cosine of theta, all I'm going to do is I'm going to come up with basically a set of points that I'm going to have, and actually I want to switch those around because I'm going to be substituting values of theta in here to find the r values. Alright, so I'm going to start by just going through and cycling through common cosine values that I know the value for. So for instance, when theta is equal to 0, I know that the cosine of 0 is 1, and 1 minus 1 is 0. So there's our radius that goes with that point. And I'm going to just generate a bunch of points to get us started here. At pi over 3, the cosine is square root of 3 over 2, so the radius is going to be 1 minus the square root of 3 over 2, which is approximately 0.134. You can calculate that on your calculator if you so choose. And then let's see, at pi over 4, the radius is 1 minus the square root of 2 over 2, which is roughly 0.293. At, sorry, that was at pi over 6. At pi over 3, so that's going to be at about 0.5. At pi over 2, the cosine is 0. It's going to be 1 minus 0, or 1. At 2 pi over 3, the cosine is negative 1/2. It's going to be about 1.5. At 3 pi over 4, the cosine is negative root 2 over 2. It's going to be about 1.707. At where am I at? 5 pi over 6. Cosine's negative square root of 3 over 2. So that's going to be about 1.866. And at pi, the cosine is negative 1. And that's going to be 2. And so I'm going to plot these points. An angle of theta, an angle where theta is 0 with a radius of 0 puts us right at the pole. At pi over 6, it's 0.134, so that's a little bit more than halfway to that first spindle. At pi over 4, it's 0.293, so that's going to be up in there somewhere. At pi over 3, it's at 0.5, it'll be right there. At pi over 2, it's going to be 1. At 2 pi over 3, it's going to be 1.5. At 5 pi over 6, it's going to be 1.866. And then the cosine values start to repeat, and I can just kind of go backwards through this. It's going to be at 1.866 when we're at 7 pi over 6. It's going to be at 1.707. Did I skip that going through? The 3 pi over 4? I did. I skipped 3 pi over 4 at 1.707. Right around there. Alright, and then 1.5 right there. And at 1 when we get to... And so I'm using the symmetry that is inherent in these cosine values to arrive at the rest of these points. And now I'm just going to draw a curve through those points. And there's what the graph of r equals 1 minus cosine of theta should look like. Alright, so let's turn to our calculator now, and we'll go to mode and change over to polar mode. And we'll look at this graph, 1 minus cosine of theta. Let's see, I'm in radians, good. I'm going to change my window up. We're going from 0 to 2 pi, that looks good, but I'm going to change. Remember, I set this up from -2 to 2 in both directions with the scale on the graph. And so we'll take a look at this graph. There's a little bit of distortion because of the width of our screen being wider than the height. And so I'm going to zoom to a square so that it normalizes that out. And there's what the graph should look like. And that looks pretty good compared to our hand-drawn graph that we had. Alright, we're going to use the calculator a little bit later. But that's how we can draw a graph of any polar function by hand. It's useful for us to know characteristics. I knew that that curve was symmetric about the x-axis because of the behavior of the cosine function. We have relationships here that talk about symmetry for polar graphs, whether they're symmetric about the x-axis, y-axis, or origin. You want to stop and think about those and kind of wrap your head around those. We can test any polar equation symmetry by replacing theta with negative theta and simplifying algebraically to see what results. So that's how we can test for symmetry. Alright, let's look at this last one. Example 4. We're going to graph these polar curves on our graphing calculator and figure out what the shortest length theta interval can be and still produce the complete graph of what we're looking at. Alright, so let's start with 2 minus 2 cosine of theta. I'll set up my window here. Let's start from 0 to 2 pi. And you know what? I'm going to put a path on this so that I can see if it's retracing itself. And I want to get everything on here. The biggest value that this could possibly have in either direction is 4, since the maximum value of cosine is 1, the maximum value of 2 cosine is going to be 2. And so let's take a look at what this graph looks like. And it draws the graph, and it stopped right when it got to the end. So a theta interval from 0 to 2 pi captures this entire graph. Just to double check, if I go to my window and I instead change the theta max to 4 pi, I'm going to get the same graph, but it's going to trace over it a second time. You can see that trace point happening there. So we knew that 2 pi was enough, and any more than 2 pi we were going to have retracing. Alright, let's try this next one. 1 minus 2 sine of 3 theta. I'll start with 0 to 2 pi. And see what happens. Whoa. We got that whole graph like that. That's a pretty interesting graph. Let me see what happens if I move that, bump that up. That looks like it might be the whole graph. Let's take a look. If we go to 4 pi. Yep, just retraces if we go beyond 4 pi. So again, 0 to 2 pi is sufficient for us to get the entire graph here. Anything less will give us less of the graph. You know, if I had done 0 to pi, I would only have gotten that part of the graph. And once I did more than 2 pi, I got more than what was graphed. And the last one here, sine of theta over 2 let's try it from 0 to pi since I already have that in as my window. See what it gives me. There's what it gives me for 0 to pi. For 0 to 2 pi, it gives me this graph, which looks like it might be the whole graph. Let's see what happens if I take it up to 4 pi. And let's see, it draws this graph. Oh, and then it keeps going. So 2 pi wasn't enough. I would have been wrong. That looked like maybe it was the whole graph, but it wasn't. I'm going to change my window coordinates up a little bit so that I can see this a little bit more clearly now that I see where it's at. I'm going to go from -2 to 2 instead. So, is 4 pi enough? Well, let's go ahead and draw the graph from 0 to 6 pi and see what happens. So there it is from 0 to 2 pi, and then it keeps going to 4 pi, and then when it goes up to 6 pi, it starts retracing that same graph. And so the interval from 0 to 4 pi was enough. So we always need to be aware when we're dealing with polar graphs. We need to be aware of the theta interval that we need to produce the entire graph of that function. Sometimes it might require a little bit of experimentation on your part. As you get more accomplished and, become more familiar with what these graphs look like, you hopefully will be able to see what a good theta interval is going to be to produce the entire graph. But if not, we always have our technology to fall back on to help us to determine what the appropriate theta interval is to produce the whole graph. Alright, that's the end of this video and the end of the lesson on graphing polar coordinates. See you guys next time. Have a great rest of your day.